Okay, we're going to talk about switches here for a few minutes, and let me bring the objectives over here for this one. Right now, 2.1 and 2.2 are the ones we're going to do here. LAN switching fundamentals, describe MAC learning and aging, frame switching, frame flooding, MAC address table, interpret frame Ethernet format. I'm going to go through the PowerPoints, and then I want to do a demo on the learning, aging, switching, flooding, and then look at the MAC address table, the things that are there. So in this one, MAC learning, frame switching, frame flooding, and then the MAC address table. A switch overview: if I could only have one new device, it would be a switch. Switches create collision domains at each port. In other words, when we talked about our bus, something goes out here, and I'm going to show you what happens in a hub, which is a bus. A couple things: we get collisions, these things blow up. In our switches, each one becomes a collision domain, and we're going to create this thing called a MAC table, media access control MAC address table, which correlates the port number to a MAC address. 3C. So we have our MAC table. 1 goes to MAC address A. I know these are not 48-bit. 2 goes to B. 3 goes to C. So if I'm going from the MAC address A to MAC address C, these ports switch themselves together, and only those two devices communicate. No possibility of collisions in full duplex. Full duplex, we can transmit and receive at the same time. 4-lane highway sort of arrangement. So creates collision domain on each port. It's a managed device, and in the demo of the iOS, how it works, you saw that we could go in and actually make changes to it. Can enable security on the ports, and we will do that a little bit later in the switch section. Can prevent some rogue devices like DHCP servers. DHCP servers are a bane to us, so we can prevent them from giving false addresses to our network. Can create virtual LANs. What we normally call a LAN will have a switch, connect a bunch of machines to it, maybe even connect some switches together, separate them with a router so that we have different broadcast domains. So a VLAN, virtual LAN, is a broadcast domain. What we do in that case is we take a switch and we divide it into LAN or VLAN 1, LAN VLAN 2, and to connect these two devices together we have to have a router because they're different. These are each an IP broadcast domain. A broadcast here and an IP broadcast here, so separate IP broadcast domains. Configured electronically, virtually, magically within the switch itself. Can configure to have individuals on the same subnet in different physical locations, and we'll do that sort of arrangement when we do VLANs, because we will have a VLAN is going to be an objective. We'll talk about VLANs and have a VLAN demo. So switch overview, it's really a neat device. It has a lot more capability than many of us use, which is usually just put it in, plug it in, walk away, leave it alone, so that we don't have to do anything. The Ethernet header we've looked at a little bit earlier, but another look at it here. The Ethernet frame is preceded by a preamble and starter frame delimiter. The preamble is just a series of ones and zeros, and it's seven bytes here in order to get the frames synchronized, or the devices synchronized. And then we have a start of frame delimiter. It's going to be 1 byte. Each Ethernet frame starts with an Ethernet header. So when we talked about the OSI model, encapsulation, we go from the top to the bottom and we keep adding these headers. We had an IP header which had the IP address. We had a TCP header, and then we are going to have an Ethernet header that is responsible for getting the information, the data, to a specific location, and the Ethernet header is going to be responsible for getting it to the destination MAC address, which is a 6-byte section of the header. Contains a source and a MAC address as its first two fields. These are the first two actual fields that we're going to use, and you notice the destination is first and then the source. And then we have a type field. What kind of Ethernet header is it? And then we have the middle section here, which is the payload, and notice the payload 46 bytes to 1500 bytes. At the end of it we have a frame check sequence which checks. This is where reliability comes in. No correction like we have in TCP, but reliability, so that if something has happened to the frame en route, it detects a frame corruption and can be dropped. So we have the data in here. The frame size, the entire frame size, the data and the header is going to be 1518 bytes. That's going to be the maximum. We're going to add 4 bytes when we do VLANs, but we'll talk about that in VLANs. The 18, 6 and 6 is 12. 14 plus 4 is 18 bytes in the 18 bytes in the Ethernet header. So when we go down here, the entire thing, if we add 18 to this, is going to be 64 to 1518. The data is going to be 46 bytes, going to be the minimum. Anything less than that's going to be called a runt, and the maximum is going to be 1500 bytes of data and padding. We add padding if we don't have enough data to get us onto a 32 byte ending of the frames. The computers like everything to be symmetrical, so we use the padding in order to make it symmetrical. Packet size, which we already did talk about. The minimum frame size for IPv4 64 bytes, which is the 46 plus 18. The header 18 bytes we've talked about. The IP header is 20 bytes and the UDP header 8 bytes, and this is how we get to where we're going with this thing. And down here is a little bit different version. 14 bytes in the source destination source and ether type, and then 4 bytes over here. 14 gives us the 18 bytes, the data 46 to 1500, which gives us the entire Ethernet frame, 64 bytes to 1518 bytes in each of the frames. A MAC address table associates a port with a MAC address, and we've talked about that. This is what one actually looks like up here. When we do it, we'll do a little red one here. We have a MAC address, VLAN, and we'll talk about VLANs. These are VLAN. Okay, maybe I won't do that. VLANs, we have a MAC address here, dynamic, which means it learned it on its own, and then the port that we're on, FA024, on down the line 122. These are the populated ports, and that means that if this is 24 and this is 2, if they go from one to the other, then the switch having the MAC addresses in its table says, oh, I have you as your source MAC address. Kind of handy having the destination in the front end. The destination, I have the destination MAC address in my table, so let me just send it there. If it's not in the address table, allow switching in hardware application specific integrated circuits. You notice that I jump around a lot, but if it's not in there, as a frame comes into the switch reads its source address when it comes in and automatically adds that port MAC address association to the MAC address table. Hence dynamic, the dynamic addressing of these. Let's see what I missed here. Create a dynamic when a frame enters the port. Yeah. MAC learning and aging. When a switch receives a frame, the following steps: the destination MAC address is compared against the MAC addresses in the table. If the match is found, the switch forwards it, and this is a big if match is found, forwards the frame only to the outgoing interface corresponding to the MAC address. It does not forward the frame to any other port, which means that we've gotten some isolation here. We've created a little bit of security with this so that somebody that comes in and puts a sniffer on the network is not going to be able to see all of the traffic. If a match is not found, the switch floods, and this is flooding and broadcast kind of tend to be the same thing. The frame out to all of the ports. So it floods it out all the ports if it's not found. Flooding says, I don't know where it goes, so I'm going to send it to everybody. And then when the answer comes back, it puts that MAC address in the MAC table because it reads the source MAC address. The default age for the MAC address entries is 300 seconds or 5 minutes. We can configure that time more or less. It is configurable if you want to turn it off. 0 disables it. But that kind of defeats the purpose of a switch, because the purpose is to one of the purposes is we want to create the isolation, create the fast switching the ports together so that we don't have to go through this finding every time with the flooding. The aging time is counted from the last time that the switch detected the MAC address. So if I have activity going on with that MAC address, it continuously resets the clock, and the MAC address stays in the switch, and we don't have to continuously find it. Flooding, switch checks, and we talked about that. The switch checks the source MAC address of the frame as it enters the port to see if it's in the table, compares it to the table entries. If there is no match, it floods or forwards the frame out all ports except the one that it entered on. If no destination MAC is found. This one compares the entries. The switch checks the source MAC address as it enters the port. If it's not there, it adds it. If not there, it adds to the MAC table. Then it checks the destination. If it's there, it sends it out. If it's not there, it floods or forwards the frame out all of the ports except the one that it entered on. And I've seen these questions where it said all the ports. It's not all the ports. It's all the ports except the one it came in on. Already knows it's not that port because that's where it came from, and it now would have an entry for that port because it had a source MAC address. When the destination enters, an entry is made into the MAC table based on the source MAC. So source MAC flooding, if it's not in the table, it floods it out all the ports except the port that it came in on. And then when we get the answer, it adds that MAC to the MAC address table. Frame switching, we're going to have 3 types of switches. The first one's called store and forward. It receives the entire frame, stores the received data in buffers until the entire frame is received, and it's going to be slower because it has to wait for the entire frame to get there. Performs a CRC, a cyclical redundancy check, before it forwards the frame, and checks the frame check sequence, the FCS, to be sure that there's not been any problems. If there's some corruption, then it will drop the frame. Ensures that frames with errors are immediately flushed. Prevents bad frames from propagating through the network. No errors are forwarded to the appropriate ports. And again here, if it has errors, it's going to drop the frames. And then TCP, that we talked about in the OSI model becomes responsible for asking for a resend. The other two types are here are what are called cut through and fragment free. Cut through is faster. It is the fastest. It forwards the frame right after it detects the destination MAC address. And if you remember, in the frame itself, the destination MAC address was the first address. So it's in the first 6 bytes. It's going to forward it. No error checks. Corrupt frames can be forwarded. It is the fastest. So the next one is kind of a combination or a mutual agreement or a compromise, I guess, of the store and forward, the full frame, and the cut through. Just detect the destination MAC address. It's faster than store and forward. It does some error checking. It checks the first 64 bytes of the frame for errors before it forwards him, and most of the errors would occur within the first 64 bytes. So what we've talked about here, we did a switch overview, what they do, what they are. We talked about the MAC address table. We talked about MAC learning and aging, how the MAC address is learned as the frame comes into the port. The switch recognizes the source MAC address, checks to see if it has an entry in the MAC address table. If it does not, it puts it there. Frame flooding: if an entry is not in the MAC address table, we're going to flood the frame out all of the ports, except the port that it came in on, in order to get the correct MAC address into the MAC table. And then frame switching is once we have the MAC addresses and we're going from a known MAC to a known MAC, then the ports are switched together in order to forward them directly to the destination device. We're going to do a demo right after this. Take a look at what happens in the switch. See you there.